Hi guys, I'm Fera from Guitars AI, and I welcome you to this gentle introduction of automatic music transcription. We will go through a step-by-step solution of a music transcription problem, which is I would like to automatically transcribe the introduction of Sweet Child O' Mine by Maestro Slash, Guns N' Roses. Um, from audio to a music score and also to Midi. We will go through the same way. There is the code in GitHub. You can run locally or you can run remotely using MindBinder. We will use basically two great Python packages. One is Librosa, which is a package for music and audio analysis. It's very powerful. There are a lot of tools that already built in. You don't need to implement by yourself. And another one that I like very much is this toolkit for computer-aided musicology. Very powerful. I think one is from the New York University. The other one is from the MIT, if I'm not mistaken. I'm also using here the Midi util, which is a Python package also to use Midi. Let's get started. If you are running locally, try to install all the requirements. I recommend you to use also a music score, which is if you're running remotely. I could not manage to configure to run music score on the remote server, so I will run here on my local machine. But music score is a very good tool for writing music scores and to play MIDI, and we will get there. So let's get started. So basically, you found me on YouTube or on GitHub. There's a link. You can launch MindBinder and start a remote server, or you can run it locally. So we'll be using here NumPy, then the packages I mentioned, Librosa, Music 21, and I also included here the Python widgets. So we will have a small graphical user interface where you can adjust the parameters. Okay, so after we done some basic configuration and imported the packages and libraries we're going to use, at this point here, I'm just defining some parameters that I may use later on. These parameters are not so trivial to set, but it's some initial conditions, let's put like this, that we can adjust later. And our first step is to load our audio file. So on the GitHub, there's a folder called audio music, which were set in the path here, where I put the introduction of Guns N' Roses' Sweet Child O' Mine. We're going to use Librosa to load this file. So I'm limiting the duration to 12 seconds because there is the introduction is before the drums and the rhythm guitar go in. So one of the reasons I chose this song is first because I think it's an excellent it's a classic guitar riff. It's cool, and for learning purposes is very good. Yeah, the notes are very separate one to each other. They're well defined. They are not on top of each other. So if you try real music to do some automatic transcription, then you get into a lot of challenges, and there is a lot of research going on for real applications on automatic transcription. But here is for you to get a feeling of it and to get the basics and concepts behind it and tools how to use it. So yeah, we are using LibRosa to load this 12 seconds of audio. So let's have a look. Let's have a listen. So yeah, there is our introduction of Sweet Child O' Mine, already loaded into an array that it's named X. So the sampling frequency of this recording was 44.1 kilohertz standard. We're importing it as mono because we just want to work with one channel. I'm setting here a duration of 12 seconds because I just want the first part of the introduction before the rhythm guitar kicks in, before the drums, the bass. So our first step is ready. Well, second step is where our first very important concept comes. And we are talking about the constant Q transform. If you're familiar with the Fourier transform, if you're familiar with signal processing, that's okay. It makes things much easier. But if you're not, well, it's not easy. You need some mathematical background, some signal processing background to completely understand. But you still can use it because LibRosa already have this tool implemented. You need to understand the parameters, how to call this function, and you understand what it returns. So you can still use it, yeah. In very general, a very general idea of the constant Q transform, as the Fourier transform, it also transforms the time domain to the frequency domain. But to understand a bit better the difference between the constant Q transform and the Fourier transform, I plotted here one graph. So we are using 128 beans. The bean numbers are here, bean 0 until bean 128. Here is our frequencies. Center frequencies are the frequencies of each bean. On the Fourier transform, we see that each bean, the frequencies of each bean are linearly spaced, and the bandwidth of each bean is constant. Yeah. The Fourier transform is very powerful. It's a very powerful tool, but it's not how actually we listen, and it's not how musical notes are related together. Yeah. Therefore, I am using here, and a lot of researchers, they also use the constant Q transform. The constant Q transform has these characteristics that the frequencies of the beans, they're exponentially separated, and the width of each bean, they're more like multiples of the width of the previous bean. Yeah, in a very general way. You can read about the constant Q transform. You should check the LibRosa documentation about how they implemented the constant Q transform. And I also recommend this website. It's called Music Information Retrieval. It's from Kama, I think is Stanford. And they have great tutorials on the music information retrieval. There is this part of the constant Q transform. So this is how it looks like. And one interesting point is like this curve here. So we have blue circles and green triangles, and they almost overlap each other. And I'm plotting the center frequency of musical notes and the center frequency of the beans of the constant Q transform. And we can see that we almost have a map that for each musical note, the frequency relates to the center frequencies of the beams of the constant Q transform, and this is what we are going to use. Yeah. So the conclusion is, let's think in very general terms. The constant Q transform can be seen as a filter bank, which each frequency of the frequency of each filter is exponentially separated, and the width of each filter is a multiple of the previous filter. There is one way how to basically understand the constant Q transform. So now we are going to use this tool. What I'm doing next is I'm defining a function to calculate the constant Q transform. So LibRosa has already this function. You just need to pass the parameters. So for example, the number of beams is a very important parameter, and also how many beams per octave. So in musical theory, one octave we can divide in 12, let's call it nodes. Yeah, C, C sharp, D, D sharp, and so on. So we're dividing each octave into 12. So by default, the beams per octave is set to 12. If you go here, the documentation, you'll see that the beams per octave is by default 12. Another very important parameter, and if you mess up with this one, everything goes wrong, is you need to set the sampling rate you're using. Yeah, this is the fundamentals of signal processing. We are using the sampling rate of 44.1 kilohertz. So we're setting it here, and we need to decide also how many beams. So we have 12 beams per octave. How many octaves do we want to use? For learning purpose, I'm using here, it's open for you to set, but the standard configuration is, it starts on C0 or C1. Yeah, the default is 32 Hertz. So it's very low. If you already know in which frequency range you are, you can set this and make it optimize it for your problem. But let's suppose we don't know what's coming, and we want from 20 Hertz to 20 kilohertz. So we're leaving like this. I'm getting the result of this function. It will return the magnitude in dB of the constant Q transform. Yeah, so for example, in this example, we have highest values in red, lowest values in blue, and check out this tutorial also from Music Information Retrieval. And our second step here then was to define a function that will calculate the constant Q transform of the array that we imported the wave file. Another step is to get this constant Q transform, and we can get a threshold of, we can set a threshold, and we set everything below this threshold to a value. Why I'm doing this? Because to detect a pitch or a note, maybe we want to get rid of a noise, maybe we want to get rid of some other harmonics that are present in the in our audio, and we want to concentrate on the fundamental frequency, for example. So this function here I created is just to, when I set a threshold, suppose the previous function will return me the maximum value would be 0 dB. So, for example, if I define the threshold is minus 40 dB, what this function does is it takes everything which is lower than minus 40 dB and sets it to a minus 120 dB. We can have a look here later on the graphical user interface, where we can adjust the threshold and we can see different things. So from this video, we've seen the constant Q transform, its relation to how the musical notes are related together, its comparison to the Fourier transform, and there is one function to calculate the constant Q transform from the audio file we loaded, and another function that will give a thresholded version of the constant Q transform. So everything which is below a certain threshold, we will set it to minus 120 dB. Okay, so this was the second step of our solution. At this point, we loaded our audio file and we applied a transformation to go from the time domain to the frequency domain, and using the constant Q transform, we can map the frequencies that we calculated into musical notes. So for example, it can look like this. At this, we have the notes, and here we have our representation, frequency representation is a time frequency representation of the audio file we imported. But before we get there, we need another thing. So we know the frequencies, but we also need to know when each musical event happens. And let's make it very similar. We need to find out where the note starts. And there is in a music information retrieval and in audio, it's called an onset detection. If you go to the musicinformationretrieval.com, they also have a tutorial on onset detection. So they explain some techniques on how to detect where the musical notes happen. So in general, it calculates a spectral novelty function, and it finds the peaks, and this tells you where the notes start. It's much more complicated than that, but let's think that it's a way to find when the notes take place. So we already have our frequency representation, our time frequency representation, using LibRosa CQT transform. So now we need to calculate an onset envelope. This is a spectral function from the constant Q transform. So I'm defining here an onset envelope using the LibRosa onset strength formula. So I'm passing the CQT that we calculated previously, and this will return me this onset strength envelope. From this onset strength envelope, we need to calculate to obtain the onsets itself. So it will search peaks and will give us the times where the musical event takes place. So these two functions there I'm using here to calculate this onset. You should read about onset detection. It's like the beginning of the musical note. So it's an interesting theory behind it. There is some tutorial on musicinformationretrieval.com by Karma. It's so for example, in my case here, I am plotting this these black lines. It's the times that are calculated when the node starts. So at this point we have a plot that is showing me on the in this axis we have the notes, yeah, which are musical notes. So it's a mapping from frequency, the center frequency of musical notes to the name of the notes. And on this axis here we have the time, and all the black lines are where each note should start. What I did is I had an intuition of the initial parameters, and then I'm using this visualization to adjust here. So I would like the onset start on the where the notes are stronger, and I would like to clean a bit, because now the algorithm still don't know which note to take. Yeah, because for example, during this interval, this time interval, we have all these frequencies present, but we would like to take just this one here. Yeah, so later on we will have to create a function that will inspect the frequencies inside this time interval, and somehow we'll decide which note, which center frequency of a musical note to take and give it a duration. Yeah, so we've seen, we loaded the audio, we calculated from time to time frequency representation. So we have an axis with the time and another axis with frequencies that we're mapping to musical notes. We are having this graphical user interface here that you can have a look at how I created. So we can fine tune, we can adjust the parameters to try to get a clear view of which. So it seems okay, it seems that it makes sense that the duration is well set here, and this is a well-defined frequency. So this is the end of this step, yeah, onset detection. So let's revise a bit. What's our problem? We want to get switch idle mine. That is an audio file. We loaded. We apply the transformation. From time, we now have a time frequency information. We calculated the onset where the notes start. So we have something like this. To go from audio to this, to the musical score, and to a Midi file, we still need some steps, and things get a bit complicated also. Yeah. So what we need when we want to define a musical score, we need to know the key of the song. We need to know the BPM that should be performed. We need to know the notes itself, and we need to know the duration of the notes. Yeah. Bear in mind that even though Librossa is a very powerful library, it's not perfect. Yeah, it's not perfect. Some tasks are very difficult, and people are still researching how to improve and optimize. Yeah, so we will not achieve 100% success, but we can get some good results. Yeah. So with this information, I would like now to calculate the tempo, the BPM of the song. Yeah, with some internet research, I found here in many places that the Guns N' Roses Sweet Child O' Mine has a BPM of 126, so it's 126 beats per minute. I've seen some more or less, but in this region. Yeah. So Librossa also have this very nice function, which is beat track. So you should read here the documentation. I believe that at music information retrieval, there's also a tutorial on beat tracking. So there's also a tutorial. They explain how some things work. So my goal is to detect the tempo, the BPM. So when I go to the score, I can set and execute the notes according to a certain BPM. So I'm defining here a function that is estimate tempo. Yeah, I'm passing the onset envelope that I calculated before, and this function will give me the tempo. So this case it calculated 130. So if you consider, I saw some places 126, 125, 128. Okay, 130, not so bad. And here I'm also introducing the Music 21 library, which will be the library that will allow me to construct the score itself. So already setting, I estimate the tempo, and I setting this metronome mark referring to this tempo. Okay, now it comes some auxiliary functions. For MIDI, sometimes you need to give the duration not in terms of seconds, but in terms of quarter notes. So this is a function that will just convert from time to beat. So it will convert seconds to quarter notes. Another auxiliary function here is in MIDI, levels goes from 0 to 127, and I'm getting there an amplitude. Yeah, it can be in dB, so a minus 120 to 0 dB, or different magnitudes, and I want to remap this to MIDI. And just as a demonstration, I am also generating with sine waves. So we have here the formula of a sine wave. We need an amplitude, and we need a duration, and we need a frequency to play, so that we can synthesize a note by constructing a sine wave that needs the amplitude, the duration, it needs the frequency. Yeah. So these are auxiliary functions that will be called inside other functions, so I can translate from time to quarter notes, from magnitude to MIDI, velocity, from so I'm defining here. So what was my goal? My goal is, now I have this time frequency representation. I want to detect for each segment which note it is. So for example, in the beginning I have that many seconds of silence because the song still didn't start. Then during this interval I want to execute this note, and I want to have a transcription, and I want to have a MIDI file, and I also want to generate a sine wave. So I will create what I'm calling here a music information array. So it will have sine wave information, and then it will have two different, and then it will have the MIDI notes. So MIDI information, it will have this music 21 information, because you need to construct this, you need to go to the MIDI Music 21 documentation and see how you need to create a note, yeah, and to give it a note duration, and then that you are able to have the transcription. By the way, to have this this picture here, you need to have the music score installed, because music score is what will the Music 21 use it to to have this picture. Unfortunately, if you're running it remotely, I could not set up in the Linux server to run MuseScore, so this, you will not show this. So what you will have, it's you can have a text information. So it's so for example, it's a music 21 note, C sharp, and these are the times that they need to be played, and this information can be converted also to Midi or to the transcription itself. So let's go back. So I need the sine wave information, amplitude, duration, frequency. I need the music 21 information, and I need the MIDI information. So what I'm doing here, I'm creating a function that is called estimate pitch and notes. I will give an array. It will have the onset boundaries, which is each segment, and we will go through each segment. It will estimate the pitch, and it will return, for example, sine and MIDI note information. Here is the function that estimates the pitch itself. It goes in each segment, and it will detect which note it is from this frequency. So this function here is the most complex. Yeah, it will take the estimated pitch and will construct my information, giving for the sine wave, it calculates the amplitude, the fundamental frequency, then it converts also to the MIDI information. So in MIDI we need the MIDI velocity, we need MIDI duration. So we need all these functions to calculate the MIDI, the sine wave, and the music 21 notes. And finally I'm creating the music information array, which puts together in an array sine wave, MIDI, and music 21 notes. So you should go through the code. It's a bit complicated, but just see the nested functions. Yeah, we're going each segment of time. We try to estimate the fundamental frequency. We're just taking averages to try to get which note we should play. We have the segment, which is the duration. We convert from dB to amplitude to give it the sine wave amplitude and to give it a MIDI velocity. And this is, we have these auxiliary functions to convert time to quarter notes, to estimate the tempo, to remap from values, and we end up with something like this. We are almost there. Yeah, it's you really should go through the code and try to understand, because it's will take too long to explain every single line. But what did we do? We imported our libraries, librosa, music 21, PyWidgets. We loaded our switch idle mine wave file. We apply the transformation from time domain to time frequency domain using the constant Q transform, that we can map frequencies to musical notes. We calculated the onsets of notes. So now we have this time frequency information with segments. We estimated the tempo. We now go through each segment, and we call a function called estimate pitch that will give us the fundamental frequency estimation for each segment. So now we have duration of a note, we know which note to play, we know what's the amplitude, what's the velocity, and we have this function that puts it all together and constructs a sine wave, a Midi, and a music 21. So it gathers all the information we have, and it places in the format required by to synthesize a sine wave, to use the Midi util library, or to use the music 21 library. In this case, the music 21 library is just taking information as we got, but the Midi, I'm using here this round to 16, so the Midi information I am rounding. So if the note is a bit more than, I'm always rounding to a 16th note. So we did it. Now I take this array, which is, I have a sine wave information, which is the index 0 of my array. So I'm concatenating all the segments together, and I will play the sweet child on mine, calculated from the constant Q transform using a sine wave, and it sounds like this. So if you think, I consider this very good results. We are taking an audio file and we are able to synthesize using a sine wave this information. Let's see now, I have also the music 21 information. To generate a score, we need to call these functions from the music 21 library. It creates a stream. I'm defining first that I want the instrument to be a guitar. I'm giving the metadata, which is the title. And it's very nice because the music 21 has this analyze key function. So it takes the notes, what we calculated before, and it will tell you which is the key. So it detected that is a C sharp major or D flat. And then I am inserting this so I can have the key in my score. So we have calculated before the tempo, we have the key, and now when I use this show string, we have this nice musical score calculated from our audio file that we use the constant Q transform, onset detection, and with music 21, for each segment we construct the note, we give it a duration, we give it a note name, a note symbol, all inside this function here. You can generate sine, Midi, and note. So it goes through each audio segment and it constructs three different information, one of which we can use music score and music 21 to have this nice music. And how does it sound? So we have here the Midi. So it's playing this score using music 21. And what we can do also, the music 21, we can write a Midi file. So is this next step. I'm writing a Midi file called Sweet Child on Mine. And now I will open music score software open this file. So let's run it. So I have here, this is the MIDI file that was saved using Music 21. This is a music score software, and now it's already set with a guitar, and it sounds like. So you can notice that the notes are not exactly according to its 16th. The MIDI information I saved, not the Music 21 notes that I saved as MIDI, but the straight MIDI information in the format used by MIDI utils. So I can use this, and I'm saving also a MIDI file, but now it's from the information in the format of MIDI utils. And I can also, this is rounded to the 16th, and I can also open Music Score. I can open this file, the switch I don't mind, and there's a difference because now I rounded to the 16th, and the when saving the MIDI, it recalculated the tempo based on the notes, and it gives me a different BPM. But now you can see that the notes are now exactly on rounded to the 16th. So that's it, my friends. Yeah, I got a bit lost sometimes, but it's this is the very basics of automatic music transcription. It's a very simple example, monophonic, the notes are well defined. Real music with things playing on top of each other is much more complicated, but you can have an idea about using the constant Q transform, a comparison to the Fourier transform, onset detection, beat tracking, how to create this user interface to fine-tune your parameters, saving to MIDI using MIDI util, having a score using Music 21. Yeah, I hope you liked it. Feel free to write me some email with some questions, complaints, and see you in another step-by-step solution of a problem, and some basic tutorials in I'm Fera from Guitars AI, Guitar Information Retrieval, and I check you later.